Hi, so welcome to the first lecture on group theory. It is a very basic course on abstract algebra and it is really useful for the students who are interested to go for something called algebraic topology, algebraic geometry, or any part where modern algebra is involved. So this is going to be the very basic frame for it. So in the first lecture, we'll be starting with a very preliminary things like we all are familiar with something called sets, right? Sets is basically collection of some well-defined elements. And we are easy to work with sets, like we can do union of two sets, we can do intersection of any two sets, we can subtract a set from others one as well. So all these things we are familiar to do with the sets. And also we know a way of transformation from a particular set to another one, that is via function, that is f is basically a relation from a to b such that each small a belongs to capital A is related to a unique element in B. So that means if I break down this condition, that is basically means that if you take any small a belongs to capital A, I will get some f of a belongs to capital B, and whenever I have any two elements in capital A which are same, then it is must that f of a and f of b must be same in B, right? That is a very basic definition of functions, and based on the functions we are easy to define something called injectivity or injective functions, also surjective functions, etc. Right? Now we will be going one step more further than this basic convention of sets. That is, now our focus will be on something called a tuple of a set and a binary operation. Okay, so first of all, let us define what is a binary operation. So binary operation means, let's consider that G is a non-empty set and star is basically a mapping from G cross G to G, a function, maybe any function. Okay, then star is basically said to be a binary operation on G, right? That means you can take any two element G1 and G2, you can send that G1 star G2, and this star is basically a binary operation, means it operates in between two particular elements in G. So as an example of binary operation, you can consider, let's say, set of integers. You can add any two integers, that is basically defined as take z1 and let's say plus of z1 comma z2 is going to z1 plus z2. Also you can multiply into integers as well, that is dot of z1 comma z2 is going to z1 dot z2. Even if we can define the same thing in case of set of real numbers, like the following, that plus of r1 comma r2 is basically r1 plus r2 dot is basically r1 cross r2 going to such that dot of r1 r2 is going to r1 dot r2. So dot means a multiplication, right? And also another kind of binary operations we can work on with let's say over q is a set of rational numbers, we can work on q cross q to q such that class is basically from q1 sorry, q1 plus q2, so like class of q1 comma q2 is going to q1 plus q2. Again, dot of q cross q is going to q, like that. Dot of q1 comma q2 is going to q1 dot q2. Okay. Also, there are more examples of where you can work with the same thing over C, that is set of complex numbers, and etc. Okay. By some more through the entire course, we'll be just getting familiar with more binary operations gradually. Okay. So that means for me, binary operation is basically a map from G cross G to G, any kind of map. Okay. Now, as we said that our main focus will be over this tuple, that is a set along with a binary operation. So this is basically is a group structure, but it should satisfy some properties. So let us define group very formally. Which is basically, let's say G is a non-empty set and star is a binary operation from G cross G to G. Okay, then G comma star, this is said to be a group if it satisfies the following properties. So that is, first of all, it will satisfy the associativity. What does this mean, associativity? Let us take any two element G1 comma G2 comma G3 belongs to capital G. First you binary operate G1 and G2 and then operate G3 with that. So that will be basically same with G1 star G2 star G3. So that means here we are basically first operating G1 and G2, then we are doing the right operation with G3 with the product, and again first in the right hand side we are doing G2 and G3 initially, and then we are doing left operation with G1 with the product. So that basically has no difference in between them, and this is true for all G1, G2, G3 in G. Number 2, there should be some identity element, that is presence of identity, that is there exists unique small e belongs to capital G such that for all small g belongs to capital G, G star E is same as E star G is basically G. Okay. Note that in general we don't have the property that G1 star G2 is basically G2 star G1. So basically what does this mean? That if we consider star is a binary operation from G1 cross G2, sorry, G1 G cross G to G. So G1 star G2 is basically given by star of G1 comma G2, which is going to G1 star G2, and G2 star G1 is basically given by this tuple G2 comma G1 is going to G2 star G1. So since these two particular G1 star, these two particular tuple, that is G1 comma G2 and G2 comma G1 may be different, that means their images in G that may be also different, right? So in general we don't have this flexibility that G1 star G2 is same as G2 star G1. But if we consider the identity element here, then we have this flexibility that we don't need to get bothered about at the side where E is getting multiplied with G or E is getting operated with G. So if E is getting operated with G from the left hand side, this is same with E is getting operated from the right side, and that will be exactly G for each of the cases. Okay, so E is said to be your identity element. And thirdly, there is something called the presence of inverse. So presence of inverse means for each small g belongs to capital G, there exists unique G inverse belongs to G such that G star of G inverse is G inverse star of G is identity. So that means note that in case of identity element, this particular small e, it is same for all the G's. So it doesn't depend on the choice of G we are considering from the group or from the set. But in case of inverse, inverse may get changed based on the choice of your element from G. So this particular G inverse is unique for each small g, but E, that is identity element, is unique for all the G's. Okay. So if it satisfies these three properties, then we call G to be a group. Okay. So as an example of groups, all the one what we have defined in so far, that is set of integers along with the binary operation plus, set of real numbers along with the binary operation plus, set of non-zero real numbers along with the binary operation dot, also set of rational numbers along with plus, set of non-zero rational numbers along with dot, set of complex numbers along with dot, set of non-zero complex number along with dot. Some more non-trivial, we can think of, let's say, set of all M, N, R. This is basically set of all matrix which is N with matrix addition, and this is basically said to be group of N cross N matrix. Also G, L and R, which is basically set of all Aij, which is where I comma j both belongs to 1 to n intersecting natural numbers, and determinant is non-zero. So this is said to be general linear group. So this is a group with respect to matrix multiplication. Okay, so these are some non-trivial examples that you can work with, and I request you to consider this an exercise to prove that each of the given steps are actually group. So you just don't need to do anything. For example, for Z, you take any Z1, any 3 points, Z1, Z2 and Z3 from this Z comma plus. Let's say you take any Z1, Z2, Z3, and you can just add them up, right? Because Z1 plus Z2 plus Z3, that is usually added up, and that basically doesn't hamper if you change the position of the elements. Also, the identity element with respect to Z plus is your 0, right? Because you take any integer here and add with 0, that actually has no effect if you consider 0 plus that integer, but the result will be exactly integer. And for each small z, in each integer, let's say small z in capital Z, if you consider minus of z from the integer, then that will be basically giving you 0. So that's why the integer is basically a group. Same will be following for same situation will be followed for r minus 0, q and q minus 0 as well. And in fact, c and c minus 0 will be the same way. And if you are very familiar with working with matrices with respect to matrix addition and matrix multiplication, then these two are not also very difficult to show. Okay. Some more kind of examples if we want to get that, maybe we can focus on finite groups. So what is a finite group? So note that if we want to say that finiteness or infiniteness, so the most obvious choice will be that should depend on the set, right? Because this group is basically a set and along with the binary operation, and in case of binary operation we don't have the, because binary operation is a function, so there is no point of working with speaking about finiteness and infiniteness. Rather we can speak about the finiteness and infiniteness of the cardinality of the set. So if you consider any group G, so G is a group with respect to binary operation star, such that so it is a group such that mod G, the cardinality of G, is infinite, so it is an infinite group. And if it is finite, then we say to be finite group. Okay, so whatever examples we have talked here, all are basically infinite groups. Also these. But if we want to speak about some finite groups, so there are some choices, like we can work on, let's say AC is basically 1, 2, 3, 4, so on up to n. Okay, so we consider G to be phasor mapping from S to S such that phi is bijection from S to S. Okay, so that means all the bijections from set of n elements to the same one is basically a group. So this is a group under the operation. The most obvious choice is a composition. Okay, so for example, it is easy to check that. Let's say you take phi1, phi2 and phi3. Sorry, this belongs to G, be any three bijections. So phi1 composition with phi2 composition phi3 of X, any where X belongs to any S, is basically same as phi1 of phi2 of phi3 of X, right? Which is basically same as phi1 composition phi2 of phi3x, right? Because you consider this phi3x to be as your x1, you can write that to be as phi1 composed phi2 of x1. So it is basically same as phi1 composed phi2 composed with phi3 of x. So this one is basically same as this one. So associativity is there. Now what is our next condition is that we need to check that identity, and as most obvious choice we can consider identity to be the identity map over S itself, that is basically S to S, such that IDS of n x is basically going to x. So for all x belongs to S, that is 1 is mapping to 1, 2 is mapping to 2, 3 is mapping to 3, dot dot up to n is mapping to n. Okay, this identity map. So identity existence is also there, right? And thirdly is that existence of inverse. So let's say phi belongs to G, so phi is basically S to S is a bijective map, right? That means we can talk about phi inverse, which is basically also from S to S is bijection, right? So that means phi composed phi inverse is identity over S, basically same as phi inverse composed phi. So this phi inverse is inverse of phi, and since inverse of a bijective function is unique, so uniqueness of course there. So that means existence of inverse is there. So G is a group, right, with respect to the composition. So we basically call this to be symmetric group of n elements, sim n. Okay. So now note that, so now the question is that how many bijections are there from S to S, right? Now let us consider here is your S, here is also your S. So now let us say 1, 2, 3, 4, so on up to n. Here we have also 1, 2, 3, 4, so on up to n. Now when we just focus on 1, if we consider any map, let's say phi is a bijection, that means phi has to be injective as well as surjective. So now 1 has n many choices, right? So 1 can map to 1 here as well, 1 can map to 2 as well, 1 can map to 3 as well, 1 can map to 4 as well, and so on. 1 can map to n as well. That means for 1 there are n many choices, right, for 1. Now let us assume that 1 has mapped somewhere in S. So then for 2, now how many choices are there? Since phi has to be injective, for 2 there are n minus 1 many choices for 2. Then for 3 again there will be n minus 3, n minus 2 many choices for 3, right? Now if thus gradually if I go on, I can get that for n there will be only one choice will be remaining for n. So that means if we now consider all the counts together, so the total number of choices is basically 1 times 2, 1, 2, 3, 4, and times till up to n. So it is basically n factorial. So the cardinality of Sn or sim n is basically n factorial, right? So that's why the symmetry group is basically with respect to composition is basically a finite group. Okay. So this is a very useful finite group, and in fact this is going to be very much helpful in further study with some properties of finite groups as well. Okay, now let us see some more construction of another kind of group, something called Z mod nz. Okay, so basically there are many ways to define the Z mod nz. So first let us go with the first way 1. So way 1 is that we define Z mod nz with the following, that it is basically 0 bar, 1 bar, 2 bar, so on up to n minus 1 bar. Okay, where each I bar is basically a set. So we'll see later that what these kind of sets are basically called cosets. Okay, and we define modulo addition is called modulo addition over plus or Z mod nz such that for any two, so how these elements will look like, A bar and B bar, where A and B both are less than Z, right? So A bar plus B bar is basically defined as, so it is 0 if A plus B is n, or 0 bar. This is A plus B minus n bar if A plus B is larger than n, and it is A plus B bar itself, the same one, if A plus B is less than n. Okay, we usually write this to be as A plus B modulo n. Okay, so now let us just verify these steps by step. So let us consider that we have chosen two particular integers less than n, right, which is A and B. Now their addition can exceed n as well, right? For example, if we take n to be as your 3 and we choose A and B, both are 2. So what is your A plus B? Is basically 2 bar plus 2 bar, right? Now we said that what is your, now it basically depends on the summation of the chosen element. So if A plus B is your n, right, is going to be 0 bar. If A plus B is larger than n, then we'll just take the difference of A plus B and n and we consider the set identified by that element. And again, if it is A plus B less than n, then A plus B bar is basically the same, like then A bar plus B bar is basically A plus B bar, right? Because anyhow we need the sum to be lie over this Z mod nz, and for that purpose we need the product or sum value of the sum should be of this form, that is 0 bar, 1 bar, 2 bar up to n minus 1. That means we need something of the form I bar where I is less than n, right? So this is for that motivation only. We are just considering if it is A plus B is n, so then we are taking, we are just dividing A plus B with n and taking the remainder. Now you see that whenever I will be taking, for any of the cases, this is going to be our basic formula for that. Okay, because you see that whenever A plus B is larger than n, then you divide, if you divide A plus B with n, this is your remainder. A plus B minus n is going to be remainder. If your A plus B is n, then if you divide a plus b with n, you are going to get remainder to be 0. If your a plus b is less than n, then you cannot divide a plus b with n, so you can trivially say that a plus b itself is your remainder. So that's why this is your basic formula to get these values: 0, a plus b minus n, and a plus b bar. Okay. So this is how one can define z mod nz. With respect to modular addition. Now the question may appear that what is 0 bar, what is 1 bar, is 2 bar, and so on, what is 1 minus 1 bar. Okay, I have said that is I bars are basically sets. Now what is basically more precise explanation of what kind of how that does this sets looks like. So for that purpose we should take the second way, that is way of 2. So let us consider a set of integers n, right? Now fix some integer n. Okay. Now with respect to this n, consider an equivalence relation, that is, let's say this one on z, this tilde on z, such that we say that a is related to b or equivalent related to b if and only if a minus b mod n is 0. So what does this mean by a minus b mod n? This basically means that n divides a minus b. Okay. And okay, first of all let us consider this relation. Now this relation will be always a equivalence relation. This is an equivalence relation. Okay, so you can check that if you take a belongs to z, then of course it is related to a because a minus a is 0 and the n divides 0, so it is reflexive. Also if you take a b to be z and a is related to b, then a minus b, this is divisible by n, so that means we can have a minus b to be your nk1. So what about b minus a? B minus a is basically n times minus of k1, right? So then of course n divides b minus a as well. So that means b is related to a. That means it is symmetric. Okay. And also if we take a, b and c belongs to z, then we have, let's say, such that a minus b is basically nk1 and let's say b minus c is your nk2, so that means a is related to b and b is related to c. So a related to b means a minus b divisible by n, and b is related to c means b minus is divisible by n. So then if we add them up, we get that a minus c is basically same as n times k1 plus k2, so n divides a minus c, which means that a is also related to c. So these basically give transitivity. Okay, so for our case, we got this to be an equivalence relation, right? So as it is equivalence relation, we can speak about the equivalence classes, that is Z of sigmas. So this Z of sigmas is basically, the equivalence classes are basically given by this class of 0, class of 1, class of 2 and so on up to class of n minus 1. Right? So what is your equivalence classes? So what is 0 bar? So 0 bar is basically set of all small z belongs to capital Z such that z is equivalent to 0. So that means you can write that to be as z is congruent 0 mod n. So, or more precisely, that basically means that n divides z. Okay. What about 1 bar? These basically stand for set of all small z belongs to capital Z such that z is related to 1, which means that z is congruent 1 mod n, means n divides z minus 1. Okay, so that means if you divide z with n, your remainder will be 1. For this case, if you divide z with n, your remainder should be 0, right? Similarly, what is your 2 bar? It's basically z belongs to z such that z is congruent to 2, related to 2, that means z is congruent to 2 mod n, or precisely n divides z minus 2, and thus we'll be just going up to n minus 1. So it's basically z belongs to integer such that z is related to n minus 1, which means that z is congruent to n minus 1 mod n, that means n divides z minus n plus 1. So now consider that, let's say any small z, any other small z, let's say any z1 belongs to z, right? Now if you divide z with n, so your remainder either will be 0 or will be 1 or will be 2 or will be n minus 1, right? So that means for any small z1, z1 will be either related with 0 or with 1 or with 2 or till up to n minus 1. And since remainder is unique, so each of these equivalence classes will be disjoint to each other, right? So that means this is the entire equivalence class for this particular equivalence relation over Z. So that's why we call this equivalence class to be as your Z modulo NZ. Okay, and this is basically your precisely 0. You can write this to a 0 bar. Equivalence class of 1, we write that to be 1 bar. So on up to equivalence class of n minus 1, we write that to be as n minus 1 bar. So now I hope that the question that arised in your mind, that what these 0 bar or the I bars basically stands for, these are precise definition of each of the sets, right? 0 bar, 1 bar, 2 bar and 0 to n minus 1 bar. And now you can check that Zn is a group. And what is the cardinality of Zn? Is basically n minus 1, right? Sorry, is basically n, because it's starting from 0 to n minus 1, it is n. So this Zn, this will be group under modulo addition. Sorry, this is modulo addition, right? Okay. Now we define something called the abelian group. What is an abelian group? Note that in a definition of group we said that whenever, let's say, G is any group and you have chosen G1 and G2 from to capital G, then there is no guarantee that G1 star G2 will be always same as your G2 star G1. That may happen for some cases, that may not happen for some elements, but it's not guaranteed that is universally true. But there are some groups where it is possible that for all G1 and G2 in capital G, we have G1 star G2 is same as your G2 star G1, right? So then G is said to be an abelian group. Okay? As an example, we can consider to be, let's say, set of n cross n matrices over R with respect to addition, set of integers, set of real numbers, R minus 0 with respect to dot, Q plus addition, Q minus singleton 0 with respect to multiplication, and etc. Okay, some non-example. The very natural choice for non-example is that because we know that at least for multiplication is not going to be abelian with respect to any in some matrices, so that's why you can think of G, L and R with respect to multiplication is not abelian, right? Because if you take any two matrix A dot B is not same as always B dot A, always, right? Okay, so far we have given some basic definitions of groups as well as some examples of finite and infinite groups, and I should mention some useful materials that we'll be following gradually throughout the course. Is basically, so I request you that you have a quick brush up with preliminary stuff like sets and functions very perfectly, bijective maps, injective maps, etc. And if you want, we will be basically following the book called Einstein and Hungerford. Both of the books are very useful for problem solving. Also, you can have a discuss with Damit and Foot as well. This is also a fantastic book and globally accepted. I mean, highly recognized and globally recognized. So these three main materials are going to be our main useful tools throughout the course, and of course throughout the lecture contains as well. Okay, so let us stop it here, and from the next time onwards we'll be discussing some more properties of groups, and also and also we'll try to induce multiplication over the Z mod nz, and also prove some lemmas. Okay, so thank you very much and see you in the next video.